This is the in-class problem. And for this problem, we're supposed to find the forces in members BC, CF, and EF. And I went ahead and drew out the truss system just for the given, labeled stuff, did the dimensions, and then I just highlighted those three members that we're supposed to find the forces of. So I start out by just checking visually for zero force members, and I don't see any here. So go ahead and look. Um, yeah, there aren't any here, mostly because there are these external forces acting on these um, at those joints. The next thing I'll do is try to figure out where, or I guess which approach I want to take, if I want to do method of sections or method of joints, or sort of how I want to approach it. So I could do method of joints. If I did that, I could start at joint D, would have two unknowns. Then I could move to joint E. That would have two unknowns, and that would give me EF, and then I could do joint C. So I'd have to do three joints to get to that. Alternatively, I could be like, okay, well, these are all in the same line, and it's just three unknowns. So I could just cut the truss here and just look at the right-hand side of the section. So, and then I really just have to do one set of equations of equilibrium versus analyzing three different joints for the method of joints. So we're going to take that approach. And remember, what we need to do is we need to sort of go ahead and make that cut and draw a free body diagram of the right hand side. Um, so we have this, we have D, C, E. We have our forces, EF, CF, BC. We have these external forces, 600 pounds, 800 pounds. We also have dimensions. So it's 4 feet, about 4 feet. That would mean that this is either a 45-degree angle, or you can do it that it's one, that the slope is 1 to 1 and square root of 2 for the common triangles. And then basically we can just start solving. So we can apply our equations of equilibrium. So we can sum the forces in the y direction, sum the forces in the x direction, and sum the moments about a point. If we sum the moments about point C, there are two unknowns at point C. We should be able to solve for EF. So we'll start with that. And some of the moments about C equals 0, we're doing as counterclockwise as positive. And so from point C, EF, the force EF is going to create a positive moment because it's counterclockwise. So we have EF times that perpendicular distance, which is 4 feet. And then that 800-pound force is going to go in the clockwise direction. So that'll be minus 800 pounds. And then that's times that 4-foot moment arm from C equals 0. So we get EF equal to 800 pounds times 4 feet divided by 4 feet. So it's just 800 pounds. And that means that we got a positive number, so that means that we picked the right direction, so it's in tension. Next, we can sum the forces in the y direction equals 0. And I picked y direction because BC is all in the x direction, so we'll just have one unknown if we do this one. So sum the forces in the y direction, we have that y component of CF. And I didn't write this. So in the C for CF, it's also, we go over 4 and up 4, so that would also be over 1 and up 1 and square root of 2. So that y component of CF would be 1 over the square root of 2 times CF. BC is in the x direction. Let's see, that's in the positive direction. 600 pounds, it goes down in the y direction. and then 800 pounds goes down, and then that EF is just in the extraction. So that equals 0. So CF equals 1400 times the square root of 2 pounds. So we got a positive number, so we were right about it being in tension. So in tension, which that equals 1,980 pounds in tension. So that's our answer for CF. And then we can sum the forces, our last equation, sum the forces in the extraction equals 0. We get EF, which is in the negative extraction, so minus 800. This is we'd solve for EF. We get CF, which is also in the negative extraction, so CF of 1400 times the square root of 2, and it's just that x component of that, so 1 over the square root of 2. Minus BC is all in the extraction, and then the 600 pound and the 800 pound force are both in the y direction, so we don't have to consider those. So we get BC equals negative 800 minus 1400, so BC equals minus 2,200 pounds. That means BC equals 2,200 pounds in compression. So the negative just means that we drew it wrong. We just drew them all in tension. So it's actually in compression. So BC equals 2,200 pounds in compression. And that would be our answers.